Massive stones stand silent across the world, monuments to a mystery that defies simple explanation. How did ancient builders raise these megaliths without modern machines? This question has puzzled experts for generations, pointing to a level of ingenuity we are only now beginning to fully appreciate. By the end of this exploration, you will understand the precise methods and brilliant teamwork that made these wonders possible. We will uncover how entire communities moved mountains of stone using only levers, ramps, and raw human determination. What forgotten knowledge allowed them to align colossal structures with the stars themselves? What does their achievement say about our own relationship with the impossible? Think of the weight pressing down, a single stone block equal to the mass of several modern cars. Moving this immense object was only the final step in a process that began deep within a quarry. Workers first had to identify the perfect stone, then carefully separate it from the living bedrock using nothing more than stone hammers and wooden wedges soaked in water to exploit tiny cracks. This was a delicate operation, a far cry from the brute force we might picture. Once freed, the multi-ton block rested in its cradle of earth, posing the next overwhelming question. How do you move a small mountain across miles of uneven ground, through forests and over rivers, without a single wheel or draft animal strong enough to pull it? The terrain itself was a relentless adversary. A single steep slope or patch of soft mud could spell disaster, trapping the stone and the hopes of an entire community. Archaeologists like Colin Renfrew point out that this was not a matter of simple brute strength. It was a highly organized communal effort, a symphony of coordinated labor where every individual had a role. The challenge of distance, weight, and landscape forced ancient engineers to become masters of their environment. They learned to read the land like a map, identifying the path of least resistance and turning natural features to their advantage. What seems like an impossible obstacle to us became, for them, an opportunity to innovate. The sheer scale of the problem makes their eventual solutions all the more brilliant. A long wooden pole becomes a tool of immense power when placed against a pivot stone. With coordinated effort, a small team could tilt a colossal block, shifting its weight just enough to slide a small rock underneath its edge. This was the lever and pivot system in action, a beautiful application of basic physics that turned overwhelming force into manageable, precise movement. It was not about lifting the stone all at once, but about winning a series of small, deliberate battles against gravity. Each tiny lift, each slight rotation was a victory. By repeating this patient process, builders could walk a multi-ton megalith across the ground or rotate it into its exact final position. This technique provided the control needed for astonishingly tight joints in structures like the dolmens of Brittany, where massive capstones rest perfectly balanced on upright stones. In Malta, archaeologists have found actual lever holes carved into the bedrock near megalithic temples, silent testimonials to the thousands of careful adjustments made here. This was engineering on a human scale, a brilliant minds-over-matter approach that required no complex machinery, only an intimate understanding of balance and force. The true genius lies in its simplicity. The lever did not fight the stone's immense weight, it cleverly redirected it. But how do you move these same stones when the journey is not a matter of inches, but of miles across harsh landscapes? This simple, ground-level technique would soon meet its greatest test in the form of epic journeys from quarry to construction site. That same ground-level ingenuity faced its ultimate test when the destination was not across the land but high above it. To lift a stone weighing many tons straight up, ancient builders turned the earth itself into a machine. They constructed colossal ramps of packed soil, mud, brick, and timber, creating a gradual, manageable path to the sky. This was not a single, universal design. engineers had to choose the best form for each project. A straight ramp, built directly against one face of a pyramid, was a direct but massive undertaking, requiring an enormous volume of material. For taller structures, a zigzag ramp that switched back and forth up one side reduced the steepness of the climb. Some researchers, studying the corners of the Great Pyramid, proposed that a spiraling ramp may have been wrapped around the rising structure itself, a corkscrew of earth that allowed teams to pull stones along a continuous path to the summit. The construction of the ramp was a monumental project in its own right. It demanded a constant supply of rubble, logs for reinforcement, and baskets of earth carried by thousands of workers. Maintaining the ramp's solid, stable surface under the immense, repeated strain of heavy sledges was a critical, ongoing task. At Teotihuacan in Mesoamerica, the very fabric of the Temple of the Feathered Serpent is embedded with evidence of these earthworks. The entire pyramid was essentially built within a giant box-like enclosure filled with rubble and soil, a permanent ramp that became part of the structure itself. Once the final capstone was set, the ramp served its last purpose. It was carefully dismantled layer by layer, its materials often recycled, leaving the pristine, geometric form of the pyramid to stand alone against the horizon. This entire process, from construction to removal, was a testament to foresight and the understanding that temporary works could achieve permanent glory. The ramp transformed an impossible vertical lift into a simple, albeit arduous, horizontal pull. It was a slow and steady victory over gravity. But what happened when there was no room for a massive earthen ramp, or when a single stone needed to be lifted with precision into a tight space? This limitation would force a different kind of invention, one that operated not on a grand landscape scale, but within the confines of the builder's own hands. The lever and the ramp solved the problem of lifting, but the challenge of distance remained immense. A stone could be perfectly positioned at the quarry, yet it was useless unless it could travel miles to the sacred site. This demanded a system for continuous motion, a way to make the earth itself carry the load. The solution was as elegant as it was effective: the sledge and roller. Visualize a massive wooden sled, a platform built to cradle a multi-ton block. Beneath it, workers placed a path of rounded logs, acting as a constantly moving track. As teams of laborers pulled on ropes, the sledge would glide forward. The key was reducing friction, and ancient builders mastered this with simple physics. The weight of the stone was distributed across the rollers, which turned freely, preventing the sled from digging into the ground. This transformed a nearly impossible drag into a steady, manageable pull. To make the system even more efficient, they turned the ground into a slick surface. Ancient Egyptian reliefs clearly depict workers pouring a liquid, likely water, ahead of a sledge carrying a colossal statue. This was not just any water, it was a deliberate lubricant. In other cultures, mixtures of mud or even animal fat were used to create a slippery film between the wooden rollers and the sled's runners. This small addition drastically reduced the pulling force required, allowing a coordinated team to move a weight that would otherwise be utterly immovable. The journey itself was a meticulously planned operation. Paths were cleared and leveled in advance, turning rough terrain into a prepared roadway. At sites like Stonehenge, the transportation of the massive sarsen stones, some weighing over 20 tons, almost certainly involved this roller method. The same principle was used to move the gigantic obelisks of Egypt, stones so tall and heavy that their movement was a legendary feat of engineering. Each successful pull was a testament to coordination, where the rhythm of the work crews and the precise placement of each new roller underneath the moving sled became a kind of practiced dance. This practical, ground-level innovation shows how ancient thinkers turned a simple observation into a world-changing technology. They saw that a rolling log moved more easily than a dragged one, and they scaled that idea up to build monuments. The steady, rolling motion across land was one thing, but what happened when the most efficient path to a building site was not over land, but directly through it via a river or a canal? This simple idea of reducing friction would soon meet its logical and perhaps most brilliant extension on the water. Water itself became a road for the impossible. When a megalith was too heavy for any sled, ancient builders turned to the one force that could bear its weight effortlessly: the buoyancy of water. In regions blessed with rivers or coastlines, they constructed rafts from bundles of reeds or lashed together logs, creating floating platforms capable of carrying stones that would have sunk deep into the earth. The stone was carefully maneuvered onto this vessel, secured with ropes, and then the water itself did the hard work, lifting the immense load and allowing it to be guided with poles or pulled by teams in canoes. This method transformed treacherous landscapes of hills and forests into smooth, navigable highways. On Easter Island, the iconic Moai statues, some weighing over 80 tons, are thought to have been transported parts of their journey on reed bundles through a network of prepared canals. At Angkor Wat, a sprawling system of canals and reservoirs provided a liquid roadmap for the sandstone blocks used to build the temple city. The builders even learned to manage water levels, using simple dams and sluice gates to flood areas and extend their floating pathways right to the edge of the construction site. This was not just transport, it was a form of alchemy, turning solid rock into a floating cargo. The grooved channels cut into the bedrock near quarries, the remnants of ancient harbors, all point to a sophisticated understanding of hydrodynamics. By harnessing the natural support of water, these engineers reduced the physical strain on their people to a mere guiding force, a gentle nudge to direct a giant already set in motion. This clever use of a fundamental force reveals a pattern, a recurring theme of using balance over brute strength. That same principle of elegant balance would soon be scaled down, from the grand expanse of a canal to the precise, controlled space around a standing stone, leading to one of the most clever lifting devices of all. A heavy stone seems to hang in mid-air, suspended not by ropes alone but by the elegant logic of a counterweight. This principle transforms the impossible into a manageable task, a seesaw on a monumental scale. Imagine a long, pivoting timber, a simple lever. On one end rests the multi-ton block you need to lift. On the other, a large container is steadily filled with sand, stones, or even water. As the counterweight grows heavier, it gracefully pulls its opposite end and the massive stone upward. This was the Shadoof principle scaled up from drawing water to raising mountains. Such a system offered unparalleled control. By carefully adjusting the amount of material in the container, builders could inch the stone upward with precision, holding it at any height needed. This was crucial for delicate operations, like settling a massive lintel onto two upright pillars at a Mycenaean citadel, or positioning the final capstone on a chambered tomb. The construction relied on materials at hand: sturdy timber for the beam and pivot, strong plant fiber ropes, and woven baskets or wooden boxes for the counterweight. The real genius was in the calculation. Through observation and likely a great deal of trial and error, these engineers learned to judge the exact pivot point and the necessary weight to balance their specific load. They were mastering the physics of torque long before it had a formal name. Experimental archaeologists have built and tested these counterweight systems, proving that a small team can lift astonishing weights with a well-designed apparatus. The evidence is often indirect. Hints in the archaeological record, like carefully placed post holes near megalithic structures that could have supported such a lifting frame. This was not brute force, it was brain force. It reveals a mind that saw the world in terms of balance and potential energy, a mind that could make the earth itself help with the heavy lifting. This sophisticated grasp of physics, turning a simple playground concept into a tool of creation, points to an even greater mastery of force and direction, one that would soon find its ultimate expression in the clever manipulation of rope and wheel. A length of twisted plant fiber becomes a lifeline to the past. While the complex metal pulley was a later invention, ancient builders possessed a deep mastery of rope itself, turning simple cordage into a powerful tool for directing immense force. They crafted these essential lines from whatever the local environment provided. In the Mediterranean, ropes were twisted from strong, flexible hemp or flax. In the Andes, builders used tough grasses or strips of leather, woven together with incredible skill. The strength did not come from a single strand, but from the way many fibers were twisted tightly together, distributing the strain and creating a durable cable capable of withstanding tons of pressure. You can almost hear the rhythmic chants of work crews, each synchronized pull translating individual effort into a unified, massive hoisting force. This was mechanical advantage in its most fundamental form. Teams would anchor ropes to sturdy wooden frames or to other megaliths already in place, creating a stable point to pull against. By directing multiple ropes from different angles, they could carefully guide a stone as it was lifted, inching it into its exact final position with astonishing control. The evidence for this is etched into the stones themselves. At sites like Ollantaytambo in Peru, you can see precisely carved notches on massive granite blocks, grooves worn smooth by the repeated passage of ropes during construction. These are the silent scars of countless lifts and adjustments. Similarly, Egyptian reliefs depict enormous statues being towed by vast gangs of laborers, all hauling on thick ropes in a perfectly coordinated effort. The true power of this system was not just in the tensile strength of the rope, but in the social strength it required. A successful lift depended on flawless communication, with signals from a foreman ensuring that every team pulled at the exact same moment. This intricate dance of human coordination turned a collection of individuals into a single, living machine. The question then becomes, what kind of society was capable of organizing such synchronized, monumental labor, and what shared belief drove them to achieve it? These seemingly simple tools were the fundamental building blocks of ancient engineering. A lever is just a rigid bar and a pivot point, but in the hands of a skilled builder, it became a device that could lift a weight far beyond human strength alone. An inclined plane, like an earthen ramp, transformed the impossible task of vertical lifting into the manageable challenge of a slow, steady pull. Even the roller, a simple log placed beneath a sledge, acted as a primitive wheel and axle, drastically reducing friction and allowing a stone to glide across the land. These were the core inventions that allowed human ingenuity to triumph over raw physical limitation. Long before the Greek philosopher Archimedes famously declared he could move the world with a lever long enough, Neolithic communities were already living that principle. They did not have formal textbooks on physics, but they possessed a deep, intuitive understanding of mechanical advantage, passed down through generations of trial, observation, and shared experience. They learned that by using a long enough lever, the force from their own bodies could be multiplied many times over. They discovered that a gentle slope made a colossal weight feel manageable. This was not magic, it was applied science. The true brilliance, however, lay in combination. A single lever could only do so much, but a team using levers to load a stone onto a sled, which was then pulled up a ramp on rollers, was orchestrating a symphony of simple machines. Each tool solved a specific part of the larger problem, and together they created a system capable of achieving the impossible. The absence of complex technology did not hinder their progress, it forced a profound creativity. With no cranes or engines to rely on, they had to look deeply at the world around them, to see the potential in a fallen log, a pile of earth, and a length of rope. This cumulative knowledge, refined over centuries, became a form of cultural inheritance. It was this very mastery of physical forces on the ground that may have enabled their most breathtaking achievements in the sky, the precise alignment of their monuments with the sun, moon, and stars. How did this hard-won engineering knowledge translate into a celestial map written in stone? The quiet precision of quarrying was an art form in itself. Before a single stone could be moved, it had to be born from the earth with immense care. Builders did not simply find a rock and start pulling. They searched for the perfect geological flaw, a natural seam or fissure in the bedrock that could be exploited. At the Aswan quarry in Egypt, the famous unfinished obelisk remains partially attached to the granite, a time capsule of the methods used. Workers would carve a series of channels along the intended fracture line, then drive dry wooden wedges into them. When these wedges were soaked with water, they would swell with tremendous force, cleanly splitting the stone along a predetermined plane. It was a patient application of physics, using tension to do the work that hammers could not. For shaping, the tools were simple yet effective. Harder stones like dolerite were used like hammers to pound and peck away at the surface, gradually roughing the block into its desired form. For a smooth finish, they turned to a simple abrasive sand. By rubbing wet quartz sand between a stone tool and the surface of the block, they created a primitive but highly effective grinding system, slowly polishing rough granite to a surprising smoothness. This entire process, from extraction to shaping, was guided by a profound understanding of the material. They knew that a stone rough shaped at the quarry was far lighter and easier to transport than a raw, irregular mass. Every pound of unnecessary stone left behind at the quarry was a pound that did not have to be hauled for miles. This preparatory work reveals a sophisticated logistical mind, one that thought in terms of the entire journey, not just the final destination. The evidence is still visible today. In the Preseli Hills of Wales, the source of Stonehenge's famous bluestones, you can see the exact sockets where pillars were pried from the earth, and discarded hammer stones litter the site like forgotten tools. These quarries were not just holes in the ground. They were the first workshops, the place where a raw piece of the planet was carefully prepared for its transformation into a monument. The legacy of this painstaking work is the endurance of the stones themselves, standing for millennia as a testament to that initial, crucial act of creation. How did these master builders then take these perfectly prepared stones and lock them together so tightly that a knife blade cannot slip between them? A stone's journey did not end when it reached the sacred site. The final, most delicate act was to join it perfectly with its neighbors, creating a structure that could defy time and tremors. Masons would spend weeks, sometimes months, carefully chiseling the faces of each multi-ton block, carving precise notches and protrusions that would lock together without a single drop of mortar. This was not just construction, it was a form of stone tailoring, crafting garments of rock that fit together with breathtaking precision. The goal was not simply to stack stones, but to make them embrace one another, distributing weight and stress so evenly that the entire wall became a single, unified entity. At the heart of this craft were specific, brilliant techniques. The mortise and tenon joint, a method more common in woodworking, was masterfully adapted to stone. Builders would carve a projecting knob, the tenon, on one stone and a perfectly matched socket, the mortise, on its neighbor. When joined, these interlocking pieces prevented lateral movement, locking the stones in place. You can see this in the great trilithons of Stonehenge, where the massive horizontal lintels are secured to the uprights with such stone tenons. Another method, dovetailing, involved carving blocks with angled, fan-shaped ends that slid together, creating a joint that resisted being pulled apart. This technique is famously displayed in the corners of Inca structures at sites like Ollantaytambo, where gigantic stones are zigzagged together with incredible complexity. Then there was curbing, the practice of shaping the bottom edge of a stone to fit over the top of the one below it, creating an overlapping bond that added tremendous stability. This meticulous work required an astonishing level of foresight. Often, stones were trial-fitted and numbered at the quarry, then disassembled for transport, a clear sign of sophisticated pre-planning. The entire process was a testament to patience and skill, with workers using simple bronze or stone chisels and abrasive sand to achieve fits so tight that, as the old saying goes, a knife blade could not slip between them. This was engineering for eternity, a deliberate choice to build something that would not just stand but endure. The desire for such permanence points to something deeper than mere structural integrity. It reflects a cultural drive to create harmony between human creation and the enduring world of stone. The true engine behind these monuments was the steady, rhythmic pull of living power. Long lines of laborers, their hands wrapped around thick ropes, leaned into the weight as one. Behind them, teams of oxen strained against their yokes, their immense strength harnessed to drag sledges that carried stones no single person could even shift. This coordinated effort of human and animal muscle was the primary force, the literal horsepower, that brought megalithic projects to life. It was a symphony of exertion, where every individual and every animal played a critical part in a much larger composition. The scale of this labor was staggering. In ancient Egypt, the movement of a single colossal statue might require the synchronized effort of hundreds, even thousands of people. To manage such an undertaking, work was organized into specialized teams, often working in shifts to maintain a constant, steady pull over days or weeks. This was not a chaotic scramble, but a highly structured operation, with foremen using drums, horns, or chants to keep everyone in perfect rhythm. The social organization behind this labor is a subject of deep curiosity for historians. Was this work a form of community service, a seasonal obligation fulfilled as part of a shared cultural or spiritual duty? In many societies, these projects coincided with periods when farming work was less intense, turning communal labor into a unifying ritual that strengthened social bonds. In other contexts, labor may have been a form of tax obligation to a central ruler, compensated with food, shelter, or other goods. The distinction is important, but the outcome was often the same, a collective endeavor that channeled the energy of an entire society toward a single, monumental goal. Consider the Moai of Easter Island, where entire clans likely participated in the ceremonial transport of their ancestral figures, or the Great Pyramids of Giza, where temporary workers' settlements housed and fed a rotating workforce on a scale that required its own complex logistics. Supporting these armies of laborers was a feat in itself, demanding a constant supply of food, water, and tools, a hidden economy built entirely around the act of creation. This incredible coordination of living power, the ability to mobilize and direct human and animal energy with such precision, speaks to a society with a clear, shared vision. It was this very unity of purpose that allowed them to look beyond the immediate, physical struggle of moving stone and turn their attention to the heavens, aligning their earthly creations with the precise movements of the cosmos. The long, slow pull of rope and the patient lift of the lever found their ultimate purpose in the silent language of the stars. Before a single stone was set, ancient astronomers spent generations watching the sky, tracking the subtle dance of celestial bodies with nothing more than horizon markers and the shifting lengths of shadows. They would drive wooden stakes into the ground, using them as simple sighting tools to mark the exact point on the horizon where the sun rose on the summer solstice, or where the full moon reached its most extreme northern setting. This accumulated data, a map written in light and shadow, was then translated directly into the layout of their monuments. At Newgrange in Ireland, a perfectly engineered roof box channel allows the light of the winter solstice sunrise to penetrate deep into the inner chamber, illuminating it for just a few precious minutes. This was not a lucky accident, it was the result of precise calculation and intentional design, embedding a celestial event into the heart of a stone tomb. Similarly, the Great Horseshoe of Trilithons at Stonehenge frames the summer solstice sunrise for those standing at the center of the circle. These alignments served as colossal calendars, marking the turning of the seasons for agricultural and ceremonial life. They also reflected a profound cosmological belief, a sense that human rituals were part of a larger cosmic order. The very act of building a structure that could capture a specific ray of sunlight once a year required planning across decades, perhaps even centuries. It speaks to a culture capable of long-term thought, where knowledge was carefully preserved and passed down so that a project begun by one generation could be completed by the next with unwavering accuracy. This celestial connection was more than just engineering. It was a spiritual act, a way of weaving the fabric of the heavens into the enduring stone of the earth. This deep spiritual drive, the force that mobilized entire communities, is the final piece of the puzzle. These silent stones were never just stone. They were vessels for a profound human yearning, a deep-seated need to connect the world of the living with the realms of the ancestors and the gods. The immense effort of construction was fueled by a spiritual imperative, a belief that these monuments served as permanent bridges between Earth and the cosmos. A massive tomb like Newgrange was not merely a resting place. It was a carefully engineered portal designed to capture the reborn sun at the winter solstice, symbolizing a cycle of death and renewal. The endless rows of standing stones at Carnac in France may have charted a ceremonial pathway, guiding the community through rituals that honored the land and its invisible forces. These structures gave physical form to a culture's most cherished values: ancestor worship, a reverence for celestial order, and a claim to a sacred territory. The stone itself was often seen as a living entity, imbued with fertility, power, or the promise of eternal life. Myths from across the world speak of stones that grew, bled, or sang, revealing a worldview where the boundary between the mineral and the spiritual was beautifully blurred. The very act of building was a ritual in itself. When a community came together to haul a multi-ton block, they were not just moving rock, they were participating in a sacred drama. This shared labor forged a powerful social cohesion, transforming a collection of individuals into a unified people with a common identity and a shared purpose that transcended any single lifetime. At sites like Göbekli Tepe in Turkey, the world's oldest known megalithic temple, the construction appears to have preceded permanent settlement, suggesting that the spiritual impulse to build came first, pulling people together and laying the foundation for civilization itself. The intricate carvings of animals on its pillars were not mere decoration. They were a symbolic language, a theology carved in stone. This deep spiritual motivation solves a practical puzzle. It explains why people would willingly dedicate their lives to such back-breaking, generation-spanning work. The reward was not material but metaphysical, a sense of place within a meaningful universe and a legacy that would endure long after they were gone. Experimental archaeology now allows us to touch this legacy not by recreating the faith, but by testing the physical methods, offering a tangible connection to the hands that shaped these wonders. A concrete block weighing several tons begins to slide across a field, pulled by volunteers straining against ropes. This is not a scene from the distant past, but a modern experiment in action, where researchers use physical reconstruction to test ancient engineering. This field, known as experimental archaeology, turns scholarly theory into tangible, often grueling practice. It provides evidence that artifacts alone cannot, revealing the practical challenges and hidden efficiencies of forgotten methods. At the French site of Bougon, teams built a wooden sledge and used a track of greased logs to move a 32-ton concrete monolith. The experiment confirmed that a crew of around 200 people could realistically transport such a weight, but it also uncovered a critical detail: the constant need for a dedicated team to run ahead, picking up rollers from the back of the sledge and placing them in front. This logistical nuance is almost never mentioned in theoretical models, yet it would have been essential for any long-distance movement. Similarly, Japanese researchers, curious about the moai of Easter Island, successfully walked a concrete replica by rocking it from side to side with ropes, a method guided by local oral history. These trials test variables like the ideal slope of an earthen ramp or the minimum number of workers needed to operate a lever system effectively. The results have been illuminating, debunking the myth that these feats required supernatural help or lost technologies. Instead, they confirm that the methods were not only possible but remarkably efficient when executed with the deep, hands-on knowledge that comes from a lifetime of experience. These experiments do more than just prove feasibility. They bridge centuries, allowing us to feel the strain on the rope and hear the creak of timber, transforming abstract concepts into a shared human effort. This hands-on insight brings us to the ultimate test case, the mysterious ring of stones on Salisbury Plain. The final journey of Stonehenge's stones is a story written across the landscape of ancient Britain. Colossal sarsen stones, some weighing over 20 tons, were hauled from quarries just 20 miles to the north. But the smaller, distinctive bluestones undertook an epic voyage from the Preseli Hills in Wales, a distance of nearly 150 miles. This was a logistical masterpiece, likely combining land and water routes. Builders may have transported these Welsh pillars on wooden sledges and rollers to the coast, loaded them onto rafts to navigate the Welsh rivers and the Bristol Channel, then brought them ashore to begin the final overland pull to Salisbury Plain. Each leg of this incredible journey required different skills, from navigating coastal waters to maneuvering sledges across soft ground. The very choice to use two distinct types of stone from such distant sources speaks to a deep cultural significance, a deliberate effort to unite different parts of the land within a single, sacred circle. Once on site, the even greater challenge began, raising the mighty Sarsens into their iconic trilithon arches. Workers first dug deep foundation pits, sloping one side to create a ramp. Using ropes and likely a massive wooden frame, they would have hauled the upright stone up the earthen slope, carefully tipping it into its prepared socket. The real genius, however, was in placing the horizontal lintel stones high atop these uprights. This likely involved building an enormous timber platform around the standing stones, a temporary scaffold that allowed workers to lever the massive capstones into position inch by painstaking inch. They carved the final, elegant touch on the lintels themselves, shaping subtle knobs and sockets so that each one locked perfectly with its neighbor, forming a continuous, stable ring. This was not just stacking stone, it was assembling a giant, interlocking puzzle of incredible weight and precision. The purpose of this immense labor shines through in its celestial alignment. The entire monument is oriented to frame the summer solstice sunrise, a fact that transforms it from a mere structure into a sophisticated astronomical observatory. The recent discovery of the Durrington Walls settlement nearby reveals a vast supporting community that gathered for seasonal feasts, suggesting Stonehenge was the heart of a vibrant ceremonial landscape. This level of coordination, spanning centuries and drawing people from across Britain, points to a society with remarkably advanced social organization. How did such a fragmented Neolithic culture achieve this unity? And what did it cost them to maintain it over generations? The true foundation of these stone marvels was not quarried from the earth, but woven from the fabric of society itself. A single visionary, perhaps a chief or a priest, stood at the center of a sprawling human machine, directing hundreds of workers with an almost musical precision. They assigned tasks not at random, but by matching individual skill and strength to the challenge at hand, ensuring that quarrying, transport, and masonry flowed together in a seamless, coordinated effort. This was not a chaotic mob, but a highly structured enterprise, a testament to a sophisticated social organization that could mobilize and sustain a workforce for years, even generations. The labor was meticulously divided. Specialist quarry workers, with their intimate knowledge of stone, identified seams and expertly split blocks from the bedrock. Teams of haulers conditioned for endurance then took over, navigating the grueling journey from quarry to site. Finally, master masons, with their patient, precise artistry, shaped and fitted each block into its final, permanent form. This level of specialization indicates a society stable enough to support people in dedicated, non-farming roles. The question of how such massive projects were funded points to complex early economies. Labor may have been a form of communal duty, a spiritual obligation fulfilled during seasons when farming work was less intense. In other cases, it might have been organized through a system of tribute to a central leader, compensated with food, shelter, or social prestige. On Malta, the incredible concentration of megalithic temples suggests that powerful, model organizations emerged to manage these island-wide efforts, coordinating the resources and labor of multiple communities. This organizational prowess was the invisible architecture that made the visible stone possible. It reveals societies with shared goals and a remarkable capacity for long-term planning, where a project begun by a grandparent would be completed by a grandchild with unwavering commitment. This generational perspective forced a deep harmony with the local environment, as builders had to carefully manage resources like timber, water, and food supplies for the workforce over decades. How did this need for long-term stability shape their relationship with the very land they inhabited, and what happened when that delicate balance was tested? Every choice of stone was a conversation with the landscape. Ancient builders did not simply impose their will upon the earth. They listened to it, selecting materials that the local environment offered and that could endure its specific challenges. In the windswept Orkney Islands, the builders of the Ring of Brodgar used a local sandstone that could withstand the relentless salt spray and driving rain, its very composition a defense against the elements. The circle itself is positioned on a narrow isthmus between two lochs, a natural amphitheater that may have amplified sound during ceremonies while being naturally shielded from the worst storms. This was not a fight against nature, but a collaboration. In forested regions, timber became the primary megalith, with massive totem poles and longhouses constructed from the abundant trees. Along tropical coastlines, builders turned to the sea, using porous but durable coral stone that breathed with the humid air. The material dictated the method, and the method honored the material. This deep environmental intelligence extended to the very process of extraction. Quarries were often worked with a light touch, exploiting natural fissures to minimize landscape scarring. At sites like the Preseli Hills, the removal of bluestone pillars left distinct, grave-like sockets in the earth, but the overall hillside remained intact, a testament to a form of prehistoric conservation. In colder climates, this adaptation took on a brilliant, seasonal form. Some researchers suggest that in northern Europe, builders might have poured water on pathways to create ice slides, transforming the challenge of winter into a slick, low-friction highway for moving stones. The massive earthen platforms of Mesoamerican cities like La Venta were not just foundations. They were carefully engineered landscapes that managed water drainage and directed foot traffic, built from the very soil beneath their feet. This holistic approach reveals a world where the boundary between the built and the natural world was fluid. A structure was not an alien object dropped onto the land, but an outgrowth of it, designed to weather the centuries in harmony with the forces that shaped it. This respectful interaction stands in quiet contrast to our modern methods, a point we will return to, but it leaves us with a profound question about the legacy of such sustainable thinking. The first attempt to move a colossal stone likely ended with it deeply mired in mud, a stubborn monument to failure. These initial setbacks were not defeats, but the very foundation of their future success. Each broken rope, each cracked lever, and each immobilized sledge taught a critical lesson about weight distribution, soil stability, and the limits of their materials. Megalithic construction was a long conversation with physics, a slow accumulation of practical wisdom passed from one generation of builders to the next. We see this process of trial and error etched into the archaeological record. At sites like the ancient Egyptian quarry at Aswan, the famous unfinished obelisk reveals a critical flaw, a fissure that appeared during extraction, forcing its abandonment. This was not a discarded mistake, but a permanent lesson left in the granite, a warning for all future engineers. Similarly, the design of tombs in Ireland shows a clear evolution, with later structures like Newgrange displaying far more sophisticated corbelled roofs and precise astronomical alignments than their predecessors. This was not a sudden leap of genius, but a gradual refinement born from observing what succeeded and what collapsed over centuries. The builders were relentless problem solvers, experimenting with different ramp angles, various lubricants for their sledges, and new ways to lash ropes to find the strongest configuration. This iterative process is the heart of practical science. They formed a hypothesis, perhaps that wet clay would reduce friction better than dry sand, and then they tested it with a real stone on a real path. The result was immediate feedback, leading to an improved method that was then preserved in oral tradition, becoming part of the community's shared intellectual property. This culture of adaptive learning allowed a technique perfected in the dense forests of Central Europe to be adapted for the rocky coasts of Portugal or the river valleys of India. The knowledge was alive, constantly being tested and refined against the unyielding reality of stone and earth. This patient, generation-spanning accumulation of know-how mirrors our own scientific method, a point of profound connection between their world and ours. Stories of giants and ancient astronauts carry a certain romantic appeal, a whisper of lost worlds and otherworldly help. These tales often suggest our ancestors lacked the intellect or skill to raise these stones themselves. Yet this very idea does a great disservice to the profound ingenuity we have already uncovered. The archaeological record holds no blueprints from beyond the stars, but it is filled with the tools, the quarry marks, and the experimental proof of human hands at work. These myths frequently emerged from a simple place. The sheer scale of the monuments made it difficult for later generations to conceive of their creation through sheer, organized effort. When early European explorers encountered the Great Walls of Sacsayhuaman in Peru, they could not reconcile the precision of the stonework with their own perceptions of indigenous capability, leading them to invent narratives of a lost, superhuman race. This cultural bias, however well-intentioned, obscures the real and far more compelling story. The evidence we have explored, from lever holes to earthen ramps, forms a consistent and practical blueprint. Experimental archaeology has repeatedly shown that the methods we have discussed are not only possible, but remarkably effective when applied by a coordinated community. The truth is, these societies did not need supernatural assistance. They possessed a deep, generational knowledge of their environment and a mastery of physics gained through patient observation and trial. Moving past these misconceptions is not just about setting the record straight. It allows us to fully appreciate the authentic human achievement. It lets us see these structures not as mysterious relics, but as testaments to what people can accomplish with shared purpose and brilliant, applied intelligence. This clearer perspective invites us to look more closely at the wisdom embedded in their work, wisdom that speaks directly to our modern challenges of sustainability and design. Our throwaway culture is confronted by a stone that has endured for 5,000 years. This longevity is not an accident. It is the ultimate lesson in sustainable design. Ancient builders were masters of low-impact construction, using materials sourced directly from the local landscape, which eliminated the need for long-distance transport and its massive energy costs. They worked with the earth, not against it, creating structures that have stood the test of time with remarkably little environmental degradation. Their entire process was a model of a circular economy where every resource was valued. Timber for sledges and levers was a renewable crop. Stone was quarried with a light touch, exploiting natural fissures. There was no construction waste in the modern sense, only materials that could be reused, repurposed, or returned to the land. This stands in stark contrast to our own industry, which generates enormous amounts of debris and relies heavily on processed materials and fossil fuels. The principles they followed are now at the forefront of green architecture. Passive solar alignment, like that seen at Newgrange, is a perfect example of using a building's orientation to capture natural heat and light, reducing energy needs. The massive stone walls of Mediterranean Nurac or Scottish Brocks provided natural thermal mass, staying cool in summer and releasing stored warmth in winter. Natural ventilation was engineered into the design of subterranean tombs and above-ground temples, creating comfortable microclimates without any mechanical systems. This is a form of ancient biomimicry, where structures were designed to function as seamlessly as a natural hill or a forest grove. They integrated with the landscape, managing water drainage through their very shape and using the earth itself as insulation. The resilience of these monuments offers a powerful challenge to our disposable mindset. They were built for permanence, not for a quick return on investment, reflecting a generational perspective that is rare today. This forward-looking wisdom connects directly to the urgent need for cultural preservation, not just of the stones themselves, but of the sustainable philosophies they represent. How do we honor this legacy not as a relic but as a living guide for the future? A gentle brush clears dust from a 5,000-year-old carving, revealing a story told in stone. This careful work is at the heart of modern preservation, a global effort to protect our shared human heritage. These ancient stones face new and relentless threats that their builders could never have foreseen. The slow, creeping damage of climate change brings more intense rainfall and temperature swings, which can crack and erode even the hardest granite. The very breath of millions of visitors can alter the humidity within a sealed tomb, encouraging damaging mold and lichen growth. More direct harm comes from vandalism, where irreplaceable carvings are scratched or defaced, and from the simple, cumulative wear of countless footsteps slowly grinding down ancient pathways. The challenge is monumental, balancing the public's right to experience these wonders with the absolute need to ensure they survive for future generations. In response, conservators employ a suite of non-invasive technologies. High-resolution laser scanning creates a perfect digital twin of an entire site, a record so precise it can measure erosion in millimeters over time. Drones map vast landscapes from above, revealing hidden features without disturbing the soil. To manage the impact of tourism, many sites now use controlled access, with raised walkways that guide visitors and protective shelters that shield delicate stones from the elements. International cooperation is crucial, with organizations like UNESCO designating these places as World Heritage Sites, which helps marshal global resources and expertise for their ongoing care. This work is deeply ethical, a dialogue between the needs of the present and our responsibility to the past. It often requires difficult choices, such as limiting the number of daily visitors or even closing a fragile monument entirely to all but researchers. Successful preservation is never just about the stones themselves. It involves the local communities who are the living custodians of this heritage. Their knowledge and commitment are the most powerful tools of all, ensuring that the meaning of these places is not lost. This careful guardianship now unlocks new chapters in the story, as ongoing archaeological work uses these preserved sites to make discoveries that continually reshape our understanding of the ancient world. A hidden landscape lies just beneath our feet, invisible to the naked eye but now brought to light by ground-penetrating radar. This technology sends pulses into the earth, painting a picture of buried history and revealing ghostly outlines of pits, post holes, and processional ways that have been lost for millennia. Around the famous Stonehenge, such surveys uncovered the remnants of a vast superhenge at Durrington Walls, a site once ringed by an incredible array of massive stones or timber posts, dwarfing the stone circle we know today. This discovery fundamentally reshaped our understanding of the area, showing it was not a single monument but the vibrant heart of an extensive ceremonial landscape, constantly changing and expanding over centuries. The story does not end there. LiDAR, a laser-based scanning system fired from aircraft, strips away the forest canopy to expose ancient features hidden below. In the dense jungles of Cambodia, LiDAR revealed a sprawling urban network around Angkor Wat, complete with canals and roads that transformed our view of the Khmer Empire's scale and sophistication. These are not just new dots on a map, they are entire chapters of human history being written before our eyes. Beyond mapping, science now peers into the very bones of the people who built these wonders. DNA analysis of remains from tombs across Europe shows complex patterns of migration and family lineage. In some cases, individuals buried with honor within a megalithic tomb came from hundreds of miles away, suggesting that these sites attracted pilgrims or skilled workers from vast distances, creating a cultural melting ice of shared knowledge and belief. Isotopic studies add another layer, analyzing the chemical signatures locked into tooth enamel and bone to trace a person's diet and geographic origin from childhood. This same technique is applied to the stones themselves. By matching the unique mineral fingerprint of a standing stone to its source quarry, archaeologists can reconstruct ancient trade and transport routes with astonishing precision. We now know, for instance, that some of Stonehenge's bluestones were quarried in Wales and then likely transported by a combination of land and water, a logistical feat that speaks to a highly organized and connected society. At Göbekli Tepe, ongoing excavations continue to surprise. The site keeps getting older and more complex, with new, even larger enclosures being unearthed, pushing back the timeline of monumental architecture and challenging our core assumptions about the rise of civilization. Each of these breakthroughs, from radar to DNA, proves that the story of the megaliths is far from finished. It is a living narrative, continually refined by technology, inviting us to see these ancient achievements not as static relics, but as dynamic creations born from a world of movement, connection, and brilliant innovation. This evolving understanding of their sophisticated methods naturally leads us to compare their ancient ingenuity with the principles of our own modern engineering. A modern engineer might run complex simulations to understand the precise forces at work in a Stonehenge trilithon. Yet the ancient builders achieved that same perfect balance through intuition and generations of hard-won experience. They understood the core principles of physics we still rely on, from load bearing and compression to the critical importance of a stable foundation. Today's skyscrapers and bridges are built with steel and concrete, but the underlying logic of distributing weight to create stable, resilient structures is a direct echo of techniques used 5,000 years ago. Both ancient and modern engineering value the prototype. Just as a contemporary firm builds a scale model to test a new design, Neolithic communities likely practiced with smaller stones, refining their lever systems and joint work before attempting their grandest monuments. This process of trial and error is the universal language of innovation. The parallels extend to teamwork and project management. Coordinating hundreds of workers to pull a sledge is not so different from managing a modern construction crew, both requiring clear communication, specialized roles, and a shared vision to achieve a single goal. This timeless approach to problem solving is especially valuable in contexts with limited resources. In some parts of the world today, builders are looking back to these ancient methods for inspiration, using locally sourced stone and low-tech solutions to create durable, disaster-resistant housing that does not depend on complex supply chains or expensive machinery. The true lesson is that innovation is not always about inventing something new, but about applying fundamental knowledge with creativity and purpose. These stone circles and pyramids are not just monuments, they are a testament to a deeply human form of intelligence, one that saw potential in a simple lever and a length of rope. This enduring ingenuity invites us to look past the stone itself and listen for the messages our ancestors carved into its very form. A carved spiral on a tomb wall is more than a decoration, it is a story told in stone. This single, continuous line winding inward speaks of a journey, a belief in the eternal cycle of life, death, and renewal that guided an entire community. These symbols were a language without words, a way to encode the deepest truths of a culture onto the very landscape they held sacred. A circle of standing stones did not just mark a place, it mirrored the perceived circle of the horizon and the cyclical paths of the sun and moon. Zigzag patterns carved into a megalith might represent flowing water, a lightning strike, or the serpentine path of the soul, each culture imbuing the same form with its own narrative. The stones themselves were chosen and shaped to carry meaning. A tall, slender pillar might be seen as a masculine form, connecting the earth to the sky, while a wide, rounded stone could symbolize a feminine presence, representing fertility and the earth itself. The placement of these stones was a powerful act, a way to claim a territory not just for a chief, but for the ancestors and the gods, weaving a spiritual claim into the land that was meant to last for all time. Look at the intricate curbstones at the entrance to Newgrange in Ireland, covered in spirals, diamonds, and arc patterns. These are not random scratches, but a complex symbolic code that scholars believe maps out cosmological principles, perhaps charting the journey of the sun or the realms of existence. In Scotland, mysterious carved stone balls, each covered with perfectly symmetrical knobs and patterns, have been found. Their purpose remains debated, but they are clearly objects of immense symbolic importance, perhaps used in rituals or as markers of status and knowledge. To understand these symbols is to hear the whispers of a forgotten worldview. It allows us to see these sites not as cold, inert rock, but as living texts filled with the hopes, fears, and cosmic wonder of the people who built them. This layer of meaning is the final, crucial piece that completes our picture of their world, a world where every stone had a voice and every alignment told a story. The principles of balance and endurance carved into Neolithic stone would one day rise again in classical marble. The post and lintel system, that fundamental act of placing a horizontal beam across two uprights, is the direct ancestor of the grand colonnades of Greek temples. While the Greeks refined the form with fluted columns and intricate capitals, the underlying structural logic of supporting immense weight with elegant stability was a lesson learned over millennia. This knowledge did not travel in textbooks, but along the same routes as traded goods and migrating peoples. A master builder from a megalithic tradition, sharing techniques at a bustling Mediterranean port, could have planted a seed that would later blossom into the Parthenon. The sheer vertical reach of Gothic cathedrals, with their soaring naves and flying buttresses, also owes a conceptual debt to that ancient desire to build toward the heavens, to create a physical testament to belief that could touch the divine. The stonemasons of medieval Europe inherited a legacy of precision fitting and an understanding of compressive force, knowledge first won by their prehistoric predecessors wrestling with multi-ton blocks. This lineage is visible in the dry stone walls of the Scottish Highlands, a vernacular architecture that uses the same interlocking principles found in Inca masonry, proving that good ideas are timeless and often rediscovered. The legacy is also woven into the land itself, embedded in local folklore. In Brittany, the aligned rows of Karnak are said to be a Roman army turned to stone by a Christian saint, a story that attempts to explain the inexplicable by grafting it onto a newer belief system. These sites became anchors for community identity, places of power and memory long after their original purpose was forgotten. Today, that same sense of awe inspires modern monument designers. The scale and stark simplicity of the megalith resonate in the Vietnam Veterans Memorial in Washington, D.C., where a simple, polished black granite wall creates a profound and somber space for reflection. The enduring power of these ancient forms reminds us that human potential, when fueled by shared purpose and perseverance, can achieve the seemingly impossible, leaving a mark on the world that echoes for thousands of years. This reflection on our shared heritage invites a final consideration of what these silent stones still have to teach us. The silent endurance of these stones is their final lesson. We have traced the path from quarry to sky, uncovering a world where levers conquered weight, ramps defied gravity, and ropes wove the strength of a community into a single, unstoppable force. This was not the work of mythical giants or lost technologies, but of human hands guided by brilliant, practical minds. Their story is one of profound collaboration and a deep, intuitive respect for the world around them. These monuments stand as eternal proof of what people can achieve with shared purpose and generational wisdom, forever challenging our modern assumptions about what is possible. As you look upon ancient stones now, see them with new eyes. Consider how their timeless principles of sustainability, of working in harmony with the earth, and the power of unified effort could inspire solutions to our own complex challenges. If this journey into the past has ignited your curiosity, we would love to hear your thoughts in the comments below. Subscribe to continue exploring history's greatest mysteries with us. Thank you for joining this voyage where every stone indeed has a story, and every story reminds us of the incredible potential within our shared humanity.